Yeah, something happened. I didn't understand what happened, but okay, now it's fine. All right. So, uh, so what was I saying? Okay, so whenever you take points, f takes them to points which are closer to each other. If you repeat this, you see you get a sequence of points which are getting closer and closer to each other, and we are on a complete metric space, right? We live in a complete metric space. Therefore, this Cauchy sequence has to converge. Okay, that's the idea. So let me write down the uh, uh, proof. Okay. Ne? Hı hı. Evet. Okay. Yeah. I'll talk about that. Okay. So you say maybe there might be more than one fixed point, right? Okay. We will see that that's not possible, but let me start with that. Okay. Uh, first, let's do the uniqueness part. Okay, my pen is not working now. Okay. All right, let me open it again. Okay. Uh, so first, uniqueness. Uh, assume that assume that uh, there are x and y in x with f of x equals x and f of y equals y. So suppose that there are fixed points x and y. Well, then by the definition of contraction mapping, right? F is a contraction mapping. Uh, then the distance between x and y, well, this is the same as the distance between f of x and f of y, because x equals f of x and y equals f of y. But this is less than lambda times dxy, right? Where lambda is a number, is the uh, contraction ratio of f, right? Whenever you have 2 points, x and y, the distance between the images is at most lambda times the distance between x and y. So there is such lambda and it satisfies this. But this means what? You see, lambda is less than 1 and dxy is something positive, right? So we obtain this. 1 minus lambda dxy is less than 0. Lambda is a positive number. It is not 0. dxy is a non-negative number because it is the distance between x and y. And the product of these two real numbers is negative or 0. Since this is positive, dxy should be 0. Otherwise, this is positive, this would be positive, so this would be a positive number less than or equal to 0. That would be a contradiction, and this implies, which implies dxy equals 0. But we know that in a metric space, if dxy is 0, hence x equals y. So what we have seen is that if I have two fixed points, we see that actually they are the same. Okay. Therefore, we can have at most one fixed point. I think this answers your question, right? Tamam. Hı hı. Ee, Yok. Uh, that wouldn't be strong enough. Uh, but okay, so you say why this, right, wouldn't be the definition of a contraction mapping, right? But this is not strong enough to prove what we are going to prove. You will see in the proof. Okay, we need something stronger. We need, uh, you know, uh, this definition to prove that. There might be some functions which obey what you said, and they may have fixed points, but for this theorem, we need this assumption. Hı. Ee, O zaman tanım zayıflar ve o hani ispat etmek istediğim şeyi yapamam o zaman. O bunu söylemiyor. O bunu söylemiyor. Bu daha kuvvetli bir şey. Orada şu var bak. X ile Y değiştikçe bu lambda sayısı birden küçük ama bire yaklaşabilir giderek. Ama ben onu istemiyorum. Ben şunu istiyorum. Bu mesafe her zaman sabit ve birden küçük bir sayı kadar azalsın istiyorum. İspatta da bunu çok kuvvetli bir şekilde kullanacağız. Senin dediğin assumption'da ben o ispatı yapamam. Okay. Well, let's see the existence. Okay. We claim that there is a unique fixed point, right? If something is unique, if there is only one of that kind of object, then it is usually easy to find, okay? The problem is when there are a lot of them, okay? Then you don't know which one to pick up. But if there is a unique point satisfying some conditions, then usually it is easy to find. Not always, but mostly. And this is one of those instances. So finding this fixed point will be very easy. How? Okay. start with any point x1 in the metric space and construct the sequence xn defined by like this. Xn is equal to f of xn minus 1 if n is larger than 2. So I start with x1. Okay, I computed I compute f of x1, I obtain another point, and then I compute f of x2 and so on, and we will see that this sequence is a Cauchy sequence, and it converges to the unique fixed point of f. Okay, so claim xn is a Cauchy sequence. Well, before I prove the claim, let me show you why this claim indeed finishes the proof. All right. Uh, uh, since xd is complete, this sequence has to be convergent. Say limit xn is equal to x0. Okay. Then I would have this f of x0, since okay, any contraction mapping is of course continuous, right? I didn't tell you that, but it is clear. You see, I want to make this is less than epsilon. If I choose my delta to be, so I want this to be less than epsilon. So if I choose my delta to be epsilon over lambda, then if dxy is less than delta, lambda times delta would be just epsilon, so that this would be less than epsilon. So you see that a continuous, a contraction mapping is continuous. So this means I can write this limit of xn, right? And goes to infinity. But what is this? F of n, f of xn is just xn plus 1. Well, this is the same sequence, right? Therefore, its limit is just x0. So we see that f of x0 is equal to x0. So that x0 is a fixed point of f. And this would finish the proof, which finishes the proof. So all we have to do is to prove the claim, proof of the claim. And let me prove this next time, since I have only like 5 or yeah, something like 5 minutes. That would not be enough to prove this. So next time I'll prove this claim, and that would finish the proof of the contraction mapping theorem. All right.